this is Dr. S.P. Arsa from Mechanical and Engineering Department, IIT Roorkee. I am going to deliver my lecture 37 on the course of the strength of materials, and this course is developed under the National Programs on Technological Enhanced Learning. Prior to start, you see this is the next lecture of the 37. You see, I would like to briefly discuss about the previous one, because you see in this also we are going to use the same theories which we have discussed. In the previous lecture, we discussed about the column and the strut, that how we can differentiate out, you see, the columns and the strut, and we could figure out that, you see, there are two main criteria through which we can make a differentiation between those column and the strut. One was the dimensional parameter, the length. You see, if it is short and thick, then it is to be a column treated as, and if it is a longer slender member and you see the thin part is there, then probably we can use the strut is there. The another which is a very important phenomena is the flexural this buckling part. Means, you see, when you apply the load, and if the buckling is there, then we can say that it is a kind of strut part is there. So that means, you see here, this buckling is is a key phenomena to differentiate out the column as well as the strut in between. And then you see, we simply discussed about that what are the the root cause for the buckling in a kind of strut part. Then we found out that there are two types of nonlinearities are there through which we can say that the buckling can be happen. One is the material nonlinearity. That means, you see, when a material is not uniformly distributed, it is, you see, a kind of isotropic part is there, and you see if one end of this strut is acted perfectly, and another end which having which is having a sort of more deflection, then probably you see the kind of buckling can be happen. The second was the geometric nonlinearity is there. That means, you see, if this strut is not uniform, there are, you see, the stub part is there, or some irregularities are there in the straightness of, you see, the strut, then probably there is a good chance of having buckling. And the third one was there, you see, when the axial load is due to the axial load, you see, if they are not exactly on the same line, they are not exactly axial. Due to that, there is a kind of eccentricity is there, and there is a great chance of the buckling. So you see here, these were the key phenomena through which we can say that the buckling can be happen, and due to the buckling, you see, we can say that this is a kind of the strut. And then you see, we simply impose certain conditions, and then we derived the Euler theory of the Euler theory is there for calculating the crippling load where the buckling can be happen. So we analyze the three different cases. The first case was when we have a pin joint. That means, you see, both ends are pin joint and the load is being applied there, and we are assuming that it is in the x domain, and whatever the deflections are coming there, it is in the y domain. So you see here, we simply set up the relation, and then we found that the crippling load where the buckling can be happen, which is known as the PE, which is the Euler particular load, is equals to pi square EI over L square. So in that we see the sensitivity of the two main parameters, as we discussed also, that one was the EI, that is the flexural rigidity, and one was the length of the this column or the strut. So this was the case where you see the pin joint was there, and we found out, you see, if you go for the higher modes of the buckling, then it is, you see, if you are going for the second mode, then we have the two waveforms are there in the particular strut, and this buckling load is 4 times of this pi square EI over L square. And if you are going for the third mode of buckling, then we have, you see, the crippling load is equals to 9 times of pi square EI over L square. So all these these modes can be easily calculated, depends on what number of, you see, this crippling loads are being considered here. That means, you see, how many number of the degree of freedoms are there for that kind of thing, and corresponding, you see, we have the value of this 2, 1, 4, 9, 16 like that, according to the pi, 2 pi, 3 pi, 4 pi like that, means in which mode which you are being to analyze the buckling load. Next, you see the case which we considered, that when we have a rigidly we have the strut, one end is rigidly fixed up and another end was free. So you see, we simply apply the free, at the free load, the load is there. Obviously, we have the maximum deflection at this particular load, and which we computed that actually if we are going up to a mean level, then the Euler crippling load for this kind of situation where one end is free, one end is rigidly fixed up, we have this PE is equals to pi square EI over 4 times of L square. And then you see the third case which we discussed, that both ends are rigidly fixed up. Means, you see, the rigid walls are there, in between we simply fix up the strut, and then you see we simply apply the load. then we found that the crippling load for this particular condition PE is equals to 4 times of pi square EI over L square. That means you see here, if you compare the pin joint and if you compare the rigidly fixed up joint, means you see the rigid ends and pin joint ends, then you see the rigid ends, it is always inducing the crippling load 4 times more than the load is there in the pin joints. So now you see here, we are going to consider in this particular chapter, again we are carrying out the same kind of analysis, but the boundary conditions are different altogether. So the first case you see where the one end is fixed and another end is pin joint, means you see here the combination says that at one end there is, where the fixed end is there is a chance of the moment, and you see when the pin joint is there is no moment application is there due to the pin joint of that. So in order to maintain the pin joint on horizontal axis, like of unloaded strut, it is necessary, because you see here obviously like we have the pin joint, so there is a kind of the unbalance can be happen. So we need to keep this unloaded strut is there. It is necessary in the case to introduce the vertical load F in the pin, so that you see we know that one end is fixed and one end is this pin joint is there. So definitely you see we have different kind of cases altogether here. So the moment of F about about the built in this particular case, then balance, and you see it is simply going towards the fixing, this fixing moment is there towards the fixed end. So now you see here we are always taking the origin at, you see the fixed end is there, and by taking that particular part we know that the load is P load is applied at both the ends, you see here these and these ends, and the moment is applied at this particular part since we are taking the origin at this particular point. So the x distance is there where the C point is there, and we have the deflection in y direction as usual, which is y, and the total length which we are taken here the L. Only the special cases, only the main case is that here not only the axial load is there, but we have, you see, the vertical load is there, just to put the necessary conditions for unloaded strut, because you see one end is free. So that's what here we are keeping these conditions. So we can see the strut with these boundary conditions where the load applications are like the x as well as the vertical part. We simply want to find out the equilibrium moment here, and we know that you see the moment can be there due to the external moment, you see the m, and there is also due to the force this F. So now you see the same standard bending equation. If you go, then we have EI into d2y by dx square is equals to minus of P into y, because of the axial load is there and we are considering at point C the y deflection, so minus P of y, plus you see here since we this up to point C, that means the distance x, this is the main influencing parameter, and then you see there is also, as you saw that in the previous figure, that the F was the vertical load was there, so we have another moment due to this particular vertical load, but the distance, effective distance is L minus x. So we can simply write the equation E into d2y by dx square is equals to minus of P into y plus F times of L minus x. So if we rearrange that part, then we have E into d2y by dx square plus P times of y is equals to F of L minus x. Or we can say that by simply dividing this EI, we have d2y by dx square is equals to plus P over EI into y is equals to F over EI into L minus x. So now you see here we want to convert the same procedure which we need to follow here, that by converting these the equation in the operational form, we have, you see, the equation d square plus n square into y is equals to F over EI into L minus x, where you see the n square is nothing but equals to pretty common stuff P over EI. So now you see here what we have simply the particular solution y particular is nothing but equals to F over n square EI into L minus x, or we can say that this y is nothing but equals to, since it is already being there this P, so we have F over P into L minus x, which is equals to y of particular integral. So now you see we need to convert to get the full complete solution as in form of generalized way. So y generalized, or we can say the y complete solution, is nothing but equals to a cos of nx plus b sin of nx plus this F over P into L minus x. So now you see we have the full solution, but again you see there are two main like the constants are there, a and b. So by with the application of the boundary conditions of, you see this, where the one end is pin joint, one end is fixed joint, again you see we need to calculate the value of a and b by keeping those conditions. So here you see the first boundary conditions which is relevant to the first case where x equals to 0, that means the fixed end is there. We know that there is no deflection because of the rigid end. So by keeping that at x equals to 0, y equals to 0, we have the first coefficient a is coming out as minus f times of L divided by p. So these two like vertical and horizontal forces are there with the corresponding distance of L. Now again you see again the same at fixed end. We know that since there is no deflection, there is no slope also because of the fixed end. So by keeping x equals to 0, dy by dx is equals to 0, we know that the value of p is coming out as f over this n times of p. So you see here we have the value of a, you have the value of b, and you have the this y particular this pi. So you see by keeping all those values here, we have the complete solution y is equals to minus f L over p of cos of nx plus f over np sin of nx plus you see this ypi, which is f over p L minus x. So you see here in these the f over np is common. So you see here you can simply say that this f over np, the complete solution y is f over np sin of nx minus you see n into L, because the n will going on top of side. So n into L cos of nx plus n times of L minus x. So you see here we have this particular condition. So now just by taking another conditions where the pin joint is there, we know that there is no deflection at the pin joint. So at x equals to L, y equals to 0, so we have NL cos of NL, you see the cos of NL because the x is now coming out as L, so n into L into cos of NL is equals to sin of NL, or we can say tan of NL is equals to NL. And we can say that you see by keeping those the values which are equating the lowest value of NL, just you see we are not going with the 0, but the lowest value of NL which satisfies this condition and which therefore produces the fundamental buckling conditions under this situation where one end is fixed and one end is pin joint, is NL equals to 4.49 radian. Just you see by taking inverse part and all those things. So now you see here by replacing this part, what we have, and we know that n is nothing but equals to square root of p over ei into L. We know that actually the length of the total cylinder part, you see the strut. So we have square root of p over ei into L is equals to 4.49 and then you see by squaring out turn and to calculate the PE value, which is the crippling, the fundamental Euler crippling load for this kind of situation where one end is fixed and one end is pin joint. And you see here to make it, you see the unloaded situation at the strut part, you see where the pin joints are there, the vertical force is being added, and due to that the fixed end, you see the moment is there. With inclusion of all those conditions, the crippling load is coming out as 2.05 pi square ei over L square. So now you see here you have a clear comparison in the two main situation. One situation was there where both ends were, you see, the pin joint. So in that case you see the crippling load was there pi square ei over L square. The one situation was there where we have both end as fixed, rigidly fixed joint. Then the crippling load was there actually as the 4 times of e square pi square ei over L square. But when you see there is a combination, that means you see when the slender members are connected in such a way that at one point we have to do the this pin joint, and at one end you see the extreme rigid end is there, that means the wall is there. So if this kind of situation is there, then you see the buckling can be happen at the crippling load, that is 2.05 pi square ei over L square. So this is, you see the situation was there. So in all 4 cases now we found that there is only the variation is there of the one part, otherwise you see it is absolutely depend on the pi square ei over L square. Now we are interested in calculating the equivalent strut length. That means you see having derived the results from the buckling load of a strut with pin ends, the Euler load for other end condition may all, or you see it can be written in the same form, where the L is the equivalent length is there of the strut and can be related to the actual length of a strut depend on the end conditions. That means you see if you are saying that this the pin ends are there and you see the other end is of any situation, maybe pin joint, maybe fixed joint, maybe anything, you see the free also. So what will be the equivalent strut length is there through which we can calculate the crippling load is. So you see it absolutely depend on what the end conditions are there of the other side. The equivalent length is is found to be like the length of the simple bow, half of the sine wave you see in the first condition, like where we know that the Struct deflection is the one curve is there. That means you see we are saying that the first mode of the deflection is there in the Struct, where we know that only the one sine wave curve is there. The buckling load for each end condition is shown therefore readily obtained, because you see depends on, you see if you are saying that the both the pin ends are there, and if you are calculating those things, then we know that in one case it is simply pi square or pi square ei over L square is there. In the second case, where you see the two the full sine wave curve is there, the two main like the heights and the peaks are there, so obviously it is 4 times, and if it is we are going the third term, then it is, you see, it is 9 times of pi square ei over L square. So all these, they like the solutions are for under the buckling load, these conditions are readily available. The use of equivalent length is not restricted to the Euler theory, and it will be used in any other like the deviations part, so which we are going to discuss later part. The critical load for columns with the other end conditions can be expressed in terms of the critical load for the hinged column, you see, where the pin joints are there, which is taken like as in a fundamental case, as you see we started from that if you see both ends are hinged or pin joints are there, then what exactly the column is there, as you see we have seen in the Struct case, and then you see corresponding changes are there, depends on what the boundary conditions which you are taken, like you see if we have a pin joint or if you have a the fixed end is there. And for C case, where you see as we discuss in that, where the column or the strut has like inflection point is there at the quarter point of its unsupported length. That means you see like in the C case, where we discussed that one end is rigid and one end was freely the free was there, and you see in that there is an inflection points are there because of like the free and load conditions are there. Then we need to like check it out that exactly like how the deflections are coming out within the unsupported part. Since the bending moment is 0 at a point of inflection at this particular way, the free body diagram would be indicates that the middle point means actually the half of that particular fixed ended is equivalent to the hinged column having effective length of LE is L by 2. Because you see, if let us say if you are comparing with the main thing, that is the both ends are pin joints, we have pi square ei over L square, and if you are comparing with the one end is free and one end is rigid, you see, then we have pi square ei over 4 times of L square. So if you are comparing the equivalent length, then we will find that the effective length will be of L by 2, because you see the 4 is coming in the denominator way, and since the L is coming as the like the total in terms of like the square term, so it is obviously, you see, L by 2 is there. So the 4 like the different cases which we have discussed here so far, in that as I told you many times, that when the first case, which was the beginning part, was there when the both ends are pinned. The second was there the one end fixed and other end is free, when the both ends are like rigidly the pin part was there. So fixed part is there, so there's the B condition, and the D condition was when the one end was fixed and other end was pinned in the previous case. So all like the possible cases which has been already discussed, and that you see we can simply figure out the equivalent length by comparing one of them. So like you see here, the first case which we discussed, the pin joint was there, and you see the axial load was coming out. So LE, simply because the PE is nothing but equals to pi square EI over L square, so we can say that LE is nothing but equals to L. The second case, you see, where we discussed about the both ends are rigidly fixed up. So obviously you see like the effective length, as we discussed in the previous slide, that LE is nothing but equals to L by 2. So obviously the PE is nothing but equals to pi square EI over this L by 2 whole square, or we can say that the 4 times of pi square EI over L square is there. And the C case, in which you see the one end which we discussed about the free end, one end is rigidly fixed up, then you see in that case we have LE is equals to 2 times of this original length. So we can say that the PE, which is nothing but equals to pi square EI over 4 times of L square. And the final case, you see here, in which one end is pin joint and one end is rigidly fixed up, we need to calculate the effective length. You see, you can see that this is the effective length in this case, which is nothing but equals to 0.7 times L. So we have, you see, the PE, if you are comparing those things, pi square EI over 0.7 L square, we have 2.05 pi square EI over L square. So the equivalent length is always important to check it out, the buckling part, that you see how the buckling can be happen, and you see what kind of sine waves are coming under the kind of load actions are there. So this was, you see, like we simply compared all those 4 situations based on the load application and what the effective length is there to check it out that part based on the Euler theory. Now we would like to compare the Euler theory with the experimental results. So we find out that there are, because you see, like these are all the computational theories are there, so obviously always it incorporates certain assumptions in that. So we can say these assumptions, as I told you in the very first part in the Struct and column, that you see if you are going towards the natural system, always it is having more and more nonlinearity is there, but if you are comparing on the mathematical way, we always incorporate certain types of assumptions. So these assumptions, you can say that these are some sort of the limitations of all those theories. So you see here that this Euler theory is also having some sort of limitations in that. So in practice, the ideal conditions are never, that means you see here the strut is initially straight and the end load being applied axially throughout the centroid is reached. That means it is not possible that you see, like in mathematically, by keeping those parametric way that okay, now this is the initially, it is the straight part is there and the load conditions are applied actually throughout the centroid part, means you see when you apply the load, it has to be applied on the centroid part, and then it will, like the point of application is towards that part only. Theoretically it is quite, you see, like logical, but experimentally you see it is not that feasible as such. You see, like, so therefore it is always somewhat eccentricity is there and the initial curvature is always coming due to the axial load. So that's what you see, I told you that we have, if you go in the realistic way, then always there is sort of the eccentricity is there, and due to the eccentricity some sort of curvature is there and the buckling are always coming in terms of that, and these factor needs to be accommodated in the required formula, which wasn't there, you see. So in every, you see, in all 4 cases which we discussed, we found that the things were quite idealistic way. Okay, we assume that the load application is there at the pin joint or the fixed joints, and it has to pass through from the centroid, and there is no, like the initial curvature is there. That means there is no, like the kind of eccentricity is there under the load applications. But you see, this part is absolutely missing in the Euler theory because it is simply based on the certain assumptions. It is realized that due to above mentioned imperfection, this is a kind of imperfection only because of the eccentricity, the strut will suffer a deflection which increases with the load, and consequently the bending moment is introduced which causes failure before Euler load is reached. So you see here we are keeping, like the crippling load at particular way, and we are saying that when the load is reaching up to this PE value, the buckling can be happen, but in a realistic way it always happen before Euler, this Euler load. Why? Because you see, because of the eccentricity, we know that there is an additional curvature is there, and you see when this load is gradually increasing, it adds, you see, the bending moment, and you see when there is an additional moment is there which we are not considering in our formula, but in practically it is being added. When the real application is there, it additionally causes, you see, the kind of moment, and then you see there is a definite failure is there before Euler load. So that's, you see, like the realistic condition is. And in fact, failure by stress rather than, you see, by buckling, and the deviation from the Euler value is more marked as this slenderness ratio, like is simply slenderness ratio means 1 by k is reduced, because slenderness ratio is somewhat, you see, like we are taking L and divided by, you see, the radius of gyration 1 by k, this L by k is there. So we have to be very, very careful that actually, like this failure is what the basic cause of this particular failure is. So somewhat we'll find that, you see, the stress rather than the buckling is, like having more deviation, and due to that, you see, like the Euler value is like more marked as compared to that particular part, and you see the slenderness ratio is always reduced in these kind of cases. So if you visualize these conditions, then you will find that these are the realistic situation which we are ignoring in our, like Euler theory or in general theories, and we have to be considered in almost all these kind of cases. So the stress to cause buckling from the Euler formula for the pin strut is somewhat, like this sigma p, which is, you see, Pe over A, or we can say that the pi square Ei over this L square, or we can say the AK square, somewhat you can say. So if we are replacing this I, which AK square, then we have the sigma E, which is nothing but equals to pi square E divided by this 1 by k or I by k whole square. So now what we have, if you look at these points, we discussed that not only this EI and L is important, but also you see this radius of gyration, the I by K, the slenderness ratio is again very important. And then if you are saying that apart from the buckling, if the stress is also one of the key feature, and you see due to that if the L by K is reducing, and if it is reducing L by K, it is in the square term and it is in the denominator, you can see that the sigma E is increasing drastically. So allowing for the imperfection of the loading and the strut, the actual value of failure must lie within, you see, like the condition which like the figure is showing here, where we have the Euler curve is there and we have the experimental curves are there, and you can see that for a like a kind of a particular material, for the structural steel, you see we have L by K, this I by K is this 80. So this Euler, there is an interaction of this particular Euler curve and the experimental part at point B, where you see like for an specific case of the structural steel, where this I by K is value of 80, we could simply figure out that in this particular plot where the sigma E versus I by K ratio is there, like this experimental part is pretty realistic way, and below this CB line, that means you see this D point here and this C point here and this B point, below this particular line we can say that these are the real actual values at the failure, and they have to be lie within this particular range. But if you are talking about the like the this computational part, which is you see the not realistic part, but is the absolutely based on the computational one with all those you see sort of assumptions, we can see that we have the high range of this like the sigma E, which is somewhat like we can say that if we approach up to that, but because of the realistic nature, always there is a good chance of failure within this particular experimental way. So this is the real term, we can say the experimental terms are there, within those we can say that yeah, there is a good chance of failure within that. So here you see as we move further, means you see the I by K ratio starting from 50 to 150, you see we have the different reasons altogether for checking out the failure theories in that. So the other formula which have like being derived to attempt the closer agreement between the actual failing load and the predicted values in this particular range of the slenderness, that means you see this I by K of 40 to I by K of 100 is the real reason where we can say that yeah, there is some sort of like the closeness is there with this particular predicted values of failure with the experimental as well as the analytical one. But again you see like with all those sort of the nonlinearity or the realistic nature, we need to incorporate the kind of nonlinearity in those terms for calculating the crippling load in the Euler theory, or we can say that we need to incorporate some sort of you see the this eccentricity, so that we know we could easily figure out that okay, if this in terms of in the microns or in terms of even the millimeter, these eccentricity is there, then how it will introduce the moment and how it will like add up in the final part of the crippling load, so as to calculate the realistic way of the buckling part. So in that you see like for that we have the first part is the straight line formula like in the other formulae. So first when we are going with the straight line formula, the permissible load is given by the formula where like the value of the index n depends on the material used and the end conditions, because you see we will find that n is nothing but equals to p square over EI. So we know that in the EI always there is a material properties are there, and also what the end conditions are there, that means how you see like whether it's a pin joint or whether it's a fixed joint or whether it's a free end like that. So this is the first simple thing is there, that we need to calculate the permissible load according to that particular formula, in which it was absolutely depend on the end. So that you see, because in almost all the equations in which you see we are simply writing in form of the operational, the d square plus n square is there. So n is an important part in that, so that you see the straight line may come as far as the permissible load is concerned. Second part is there, that is the Johnson parabolic formula in this curve, where you see the Euler part is there. So in that Johnson parabolic form, since as its name is there, it has a side kind of parabolic nature. So we can simply define this P as you see the sigma y a into 1 minus you see n into I by K, where you see we have an index b, because you see in that we have some sort of the index is there, which is absolutely depends on the n conditions, and through which you see by introducing this n which is being replaced by this index, we have some sort of the value for this Johnson parabolic equation as p is equals to sigma y into a 1 minus b. Now it is being replaced because n is nothing but equals to b times of I by k. So when we replace this index, it has, you see, the final formula sigma a into the sigma y into a 1 minus b times of I by k whole square. So it has, you see, a kind of parabolic in the nature. The third formula which you see in that particular approximation is the Rankine-Gordon formula. So you see here Rankine-Gordon formula says that, you see, this p, 1 of p Rankine is nothing but equals to, we have 1 by pe plus 1 by pc. So PE is nothing but, you see, as usual we are taken that as a Euler crippling load, but in that, you see, we need to add the crushing load, or we can say the yield point in the compression, and PR is the actual cause of failure. So you see here what this Rankine says, that you need to add certain additional part in the realistic way, because you see it is always be there, the crushing load is always be there under the compression, or we can say that there is an additional yield point is there due to the compression part. So by incorporating that, now we can go, we can go up to a closer part of the realistic part. So that's what you see, 1 by PR, which is the real, or we can say the actual load is there which caused the failure, or we can say the Rankine load is nothing but equals to 1 by PE or plus 1 by PC. So for a very short, this strut where PE is very large, hence 1 by PC would be large, so that 1 by PC can be, easily neglected in that term. Because we know that 1 by PE is always an important feature is there in general cases. Thus PR is equals to PC for very large strut. So again, you see, now we have to be very careful that if we are talking about a large strut, then P realistic is always be equals to PC, because you see the whatever the crushing load is there, it is the main responsible for the large strut which incorporated, you see, the buckling part. So PE is very small, so 1 by PE would be large, and we can say that 1 by this PC can be easily neglected. So we have PR is equals to PC for the large strut. But as far as very small struts are concerned, we have we need to focus on this particular PC part, and the 1 by PE would be an important consideration in these cases. So either the large strut or the short strut, how these the crushing load or the Euler load is responsible for these kind of things. So they have to be calculated in the actual load which is causing the failure in the strut. So the Rankine formula is therefore valid for extreme values of 1 by this I by k, and it is also found to be fairly accurate for the intermediate values in the range under the consideration, because you see it is always related to that for this small or for large, which load is real responsible for causing the buckling part. So that's what you see, it is somewhat more accurate than other formula. So with that, you see, now if you are going for 1 by sigma into A, which is equals to 1 by sigma E into A plus 1 by sigma Y into A. So now you see, we are fairly in that particular portion, so that we can say that 1 by sigma is nothing but equals to 1 by sigma E plus 1 by sigma Y, or we can say that we can simply calculate the responsible sigma in those cases. So in the Rankine formula, so we have sigma, which is nothing but equals to the final equivalent strength, this buckling stress is there, is nothing but equals to sigma y divided by 1 plus sigma y by sigma E. So these, you see, these are the crucial things are there in that cases. So now for the strut with the both ends are the pin part, we know that it is nothing but equals to sigma E pi square EI into pi square EI by L square was there. So now by replacing those things, what we have in the this I by k formula, we have pi square E divided by I by k whole square, or now you see if we are keeping that part particular here, the sigma, then we have sigma is nothing but equals to sigma y over 1 plus sigma y pi square E into 1 by k I by k whole square, or we can say now if you are replacing this by a constant A, and this constant is nothing but equals to sigma y over pi square EI, and you see now we have the final value of sigma, which is a realistic way, as compared to the Euler one, is sigma is equals to sigma y, which is, you see, sigma y is the yield point, the stress divided by 1 plus A times of I by k whole square. So where a is equals to sigma y or pi square ei, and you see the value of a is found by conducting experiments on the various materials, because you see ei is depends on the material. So what material which we are using, and like what kind of shapes are there. So it's absolutely sensitive to the material property which we are using theoretically, but like having a value normally found by experiments for variety of the materials. So you see here in those cases we simply calculated that like if we have the 4 different means like the experimentations are there and the theoretical values are there, if they have the deviation, then how we can like match those values. Then we simply concluded that yeah, if you see like there is this comparison is there in between those terms, then we can simply adding some nonlinearity, or we can simply adding some correction factor to keep those values in a closer way. So that's what you see all these, either the Rankine, or either you see this a parabolic term, or either you see the straight line terms. All these terms are being added just to verify those results, and hence we can say that we have the Rankine load. This is nothing but equals to like divided by area, it is there. So sigma Rankine load is equals to sigma y into a divided by 1 plus a over I by k whole square. And typical values of a, which is a real constant, is there in the Rankine formula, are simply we can take as per you see what kind of load conditions are there and what is the material property. So if you look at this particular column, then you will find that we have the material column here. So we are using 3 different materials. The low carbon steel is there, the cast iron is there, and we have the timber. So you see like right from ductile to brittle material, we have all those kind of things are there, and we can simply use like sigma y or sigma crushing parts is there in terms of mega Newton per meter square. So you see it has the value clear of sigma y, which is 315 in case of low carbon steel, 540 in case of cast iron in the real like the brittle material, and in timber also it is a least value, that is the 35. So now you see here, and again as I told you, since it is absolutely the value of a is depends on what exactly like the load conditions are there. So if you see like if we have the pin joints at the extreme ends of these, then you see that we have the value of a is 1 by 7500. And if it is for the low carbon steel, and if this value of a for cast iron is 1 by 1600, and 1 by 300 is just for the timber part. So this is the condition where the pin joints are there, but if we have the fixed ends, means the resultant fixed ends are there, then 1 by a value for like these materials are much higher than these, because you see now we have the rigidly fixed ends are there. So obviously you see the kind of movements in those terms which we are assuming in the numerical values are real different than the actual one. Because you see some sort of moments can be happen, some depends on what kind of you see the rigidness is there. So for that you see like we need more like values in those terms. So we have you see like we'll find that for low carbon steel we have 1 by like the 30,000 is there when the fixed ends are there for low carbon steel of value of a. For cast iron, the value of a for fixed end is 1 by 64,000, and for you see for timber we have 1 by 12,000 is there of value of a for these things. So depends on you see the how much like the flexibility is there more. So it depends on the flexibility of part. Like we can see that if the more like rigidly fixed joints are there, then probably see we don't have more flexibility towards that. So it has a like we can keep the value of a will be in a laser position, while in the pin joints you see more and more flexibilities that can be introduced in this particular kind of systems. So obviously as compared to the fixed joints we have like the higher values of these things for different kind of materials. But you see like as far as the low carbon steel is concerned, based on the microstructures and based on the kind of load conditions, always we have higher values of these values as compared to the timber part. And cast iron, since like it is providing like it's a brittle material, so it is more harder materials are there. So somewhat like it has not exactly like we can say the laser values are there as compared to the ductile material of this low carbon steel of the value of a. So you see here, so this was the correction when the, like when we know that there is like the n is not exactly matching with those particular values. So the a will come. But now you see if like because of the eccentricity there we know that there is an additional kind of moment is there. So we need to add that part. So by like introducing the initial curvature in the strut, then like we again goes towards like the realistic conditions that yeah, now initial because in the realistic way we have the initial curvature is there, or because of the eccentricity. So by adding directly in the numerical values, can we really go towards these things? We just want to check that part. So here you see, in this case we have the strut with the initial curvature. So you see here we are simply approximating the curvature radius r0, which is equals to 1 by d2y0 by dx square. Initially you see we are considering d2y by dx square at the y0 condition, means you see when there is no load conditions are there and we have initial curvature. So by adding that, you see we have this r0 values, and now by taking the same conditions of the bending moment, m is nothing but equals to m by I is equals to E by R in this particular curvature length in the bending of beam. So EI by R will give you exactly the moment which is being there initially. With that consideration, here we have B over 1 by R minus 1 by R0 is equals to m. Since the straight is having some initial curvature as we have considered here, now we need to put 1 by R, which is d2y by dx square, or 1 by R0, which is d2y0 by dx square. So we can see that this R, which is a realistic condition, is coming under the load conditions, and R0 which simply introduced because of the initial conditions, just to compensate that, when the load is not exactly on the center line and due to the eccentricity the things are there. So now you see here where the y0 which dy0 by dx square was there for r0, y0 is the value of the deflection before the load is applied to the strut, and when the load is applied to the strut we have the deflection which is increases to the y. So with that consideration, what we have the resultant part is there. So EI into d2y by dx square minus d2y0 by dx square is giving you the real value of m, or if you multiply those things, we have EI into d2y by dx square minus EI into d2y0 by dx square is equals to m. Or if you compare those things, then we have probably EI into d2y by dx square, which is exactly equals to m plus EI over d2y0 by dx square. So now you see here, if you are saying that the pin joints are there and due to the axial load condition we have the moment which is P minus P into I. So now if we are comparing those things, then what we have EI into d2y by dx square. Now we can simply replace this m by minus pi, so it is equals to minus pi plus EI into d2y0 plus d2y0 over dx square. So in that particular pin strut where you see the pin joints are there, the bending moment is always it is coming in that particular this way. So we need to consider minus py in terms of the m. So with that particular consideration, what we have now d2y by dx square plus p into y over EI is equals to d2y0 over dx square. So we know that the n square is always p over EI. So by equating that, what we have the second order differential equation in terms of d2y over dx square plus n square y is equals to d square y0 over dx square. So this is the new second order differential equation which is having the initial slope plus the slope is increases due to the load conditions. So the initial shape of the strut y0 may be assumed to be circular, parabolic or sinusoidal without making much difference to the final result, but most convenient form is here in terms of the c which we are considering, y0 is c times of sinusoidal this n into x over I, which satisfies the end conditions and the corresponding to a maximum deviation at point C. So any other shape would be analyzed also by Fourier, the series is there, then we can say that d2y over dx square plus n square y is equals to d2y0 over dx square. So by keeping those in the most convenient form of the sinusoidal form, because there is the periodic phenomena are there. So what we have d2 over dx square in terms of c into sine of pi x by I is equals to minus c pi square by I square sine of pi x by I. So you see the computational solution which can be easily getted by the two forms. One, the general solution is y complementary function and y this particular integral. So you see by keeping those things, what we have y equals to a cos nx plus b sin nx plus this which we have discussed, c into pi square over I square divided by pi square over I square minus n square sin times of n pi x over I. So now you see here, by keeping those boundary conditions, we can simply get the real solution of the generalized part. So we have boundary conditions in the relevant problem is at x equals to 0, obviously there is no deflection is there. So it gives you a clear cut indication of b equals to 0, where you see where x equals to L, the extreme condition we have y equals to 0. So by keeping those conditions we have, or we can say at x equals to this L by 2 also, there is no slope conditions are there. So for all those conditions we have the b equals to 0. So the complete solution will give you y equals to c times of pi square over I square divided by pi square over I square minus n square sin times of pi x over I. So the basic equation was the PE, which was pi square or EI by L square was there. So now we just want to compare both the equations in those terms. So here we have the new term in the first equation, which was y equals to c into pi square y L square divided by that. So what we have in those terms, we have pi square over L square divided by pi square over L square minus n square. So we need to, in that case only, we are missing about the EI. So we need to multiply the EI with denominator and this numerator. Then we have the new form of the equation, which is pi square EI over L square divided by pi square EI over L square minus n square EI. So you see, which is equated by the both of the condition PE over divided by PE minus P. So what we have in this case, we will find that in this particular the crippling load, there is a difference part is there in the denominator part. So by comparing those n square, which is nothing but equals to P over EI, we have the Euler load PE, which is the crippling load was there, and the P was the applied load. If you compare all of them, then we have y, which is the new term, y is equals to c times of pi square over L square divided by pi square over L square minus n square sin times of nx over this L. So you see here, if you compare both the things, then what we have c times of PE divided by PE minus P sin of pi x over L, or we can say that the crippling load which was there in that case was pi square over EI into L square. P you see here is the applied load is there, that how the axial load which is to be there, which is causing the deflection in this case is, and you see here we have n square, which is nothing but equals to P square over the P over EI. So incorporating all those values, we have the new term which is coming due to the initial deflection consideration, that okay, now we have the initial deflection, the radius of curvature r0 is there at d2y 0 over dx square. With all the consideration, we have the new term, and that's why you see always in the realistic term we found that the failure is there before the this particular part. So here in this case, the bending moment for a pin ended strut at any point can be easily given as minus p times of y, and the maximum bending moment is always at the somewhere where the maximum deflections are there, so p times of y maximum. So in order to define the absolute value in terms of the maximum amplitude, now we are using the kappa word, the cap is there. So in terms of the cap, if we are incorporating that part here, so what we have the realistic way, m cap is equals to p times of y cap, and we know that it is nothing but equals to c times of p times of PE divided by PE minus P, because you see we got that particular term in that case in the initial curvature conditions. So we have m cap is equals to PE divided by PE minus P, where y maximum is nothing but equals to PE over PE minus P. And you see here sin of pi x by L is equals to 1 in this the maximum loading condition case. So we have pi x over L is equals to pi by 2. So we have the real the bending moment case in which the initial curvature is being considered is CPPE divided by PE minus P. So in all these cases, we found that you see here that if you are comparing the experimental results with this particular Euler theory, then there is a great difference is there in between all. So again you see in the next lecture we would like to continue these cases, so that you see what other parameters are there which can be incorporated to calculate the realistic values of the failure, so that you see when we are predicting about the failures of the strut or the column, then always we are reaching to the real values of that rather than you see the numerical value or the computational value which is far ahead from the real, or we can say the experimental value of the buckling load. So you see here in this lecture we mainly discussed about those, and we found that there were two main the phenomena were there. First, you see there is always an eccentricity is there in these structures, and due to that the additional bending moment is always applied, and you see you need to consider those additional moment is there, which we were ignoring in the Euler theory. So here the additional R0 was added, and we found that this m value was Cp into Pe divided by Pe minus P. So you can see that how the what the great influence is there of the difference Pe minus P, because you see here whatever the values are coming, they have the direct influence on the bending moment. In the second case which we discussed which wasn't considered in the Euler theory was, you see what is the material properties there. So based on that, you see these the slope conditions are always deviating from that, and that's why you see the 1 by a means, you see in the different formulas we are considering like in the Rankine formula or in this Gaussian formula. So whatever the things are coming, accordingly we need to consider with those things. So in the next lecture, you see we are going to discuss about more the realistic nature of these Euler or beam theory. This Euler and Struct theories are there for calculating the real values of these buckling load, and then you see whatever the safer designs are there, accordingly we need to consider the factor of safety for that. Thank you.
Thank you.